In the realm of modern electronics, semiconductors are the mini heroes powering our daily lives, from the smartphone we use to space satellites. These materials form the backbone of countless devices, enabling the processing and storage of information at unprecedented speeds. Silicon, the most widely used semiconductor, has been the cornerstone of this technological revolution, giving rise to the age of information. However, as we continue to push the boundaries of miniaturization and performance, silicon is approaching its physical and practical limits. The relentless pursuit of Moore's Law, the observation that the number of transistors on a microchip doubles approximately every 2 years, has led to the research of alternative materials that can sustain the momentum of innovation. We introduce a new material called carbon nanotubes exhibiting semiconducting behavior depending on their specific structure. Let's delve into semiconductor nanotube, exploring their properties, structure, and the transformative potential they hold for the future. Semiconducting carbon nanotubes are tiny, tube-shaped materials made of carbon atoms arranged in hexagonal pattern. What makes What makes them special is how their structure affects their properties, especially their ability to act like semiconductors. They allow electrons to move very quickly and with almost no resistance, and in very short tubes, electrons can even travel without bumping into anything, making them super fast for use in transistors. These nanotubes also have optical properties, meaning they can absorb light strongly at a certain wavelengths and even glow when hit by light. This makes them useful for solar cells, sensors, and medical imaging. Mechanically, they are incredibly strong and flexible, stronger than steel by weight, and can bend without breaking, which is great for making tough, flexible materials. Thermally, they can carry heat very well and stay stable even at high temperatures, which is used for cooling electronics. Chemically, they are stable in many environments and their surface can be changed to attach to other molecules, which is helpful in drug delivery or chemical detection. Altogether, these amazing properties make semiconducting carbon nanotubes a promising material. Carbon nanotubes are materials made entirely of carbon atoms that are arranged in hexagonal pattern, similar to a sheet of graphene, but rolled up into a tiny hollow tube. These tubes are incredibly small, thousands of times thinner than a human hair, but they are also extremely strong, light, and have unique electrical and thermal properties. Carbon nanotubes were discovered in 1991 by Japanese scientist Sumio Ijima while he was studying carbon-based materials using a high-resolution transmission electron microscope. During an experiment involving an electric arc discharge between two graphite electrodes, a method commonly used to produce fluorescence, Ijima noticed strange needle-like structure in the carbon suit that formed. Upon closer examination, he found that these structures were made of concentric layers of graphene rolled into seamless cylindrical tubes, which he later named multi-volt carbon nanotubes. This accidental discovery sparked huge interest in the scientific community because the tubes showed exceptional mechanical strength, electrical conductivity, and thermal stability at the nanoscale. The hexagonal arrangement of carbon atoms in carbon nanotubes originates from their fundamental building block, graphene, which is a single layer of carbon atoms bonded in a two-dimensional honeycomb lattice where each carbon atom is connected to three others through strong covalent bonds. This hexagonal pattern is the most efficient way to arrange atoms in a plane, minimizing energy and maximizing stability. Carbon nanotubes are composed of carbon atoms arranged in a hexagonal pattern. Each carbon atom in this arrangement is bonded to three neighboring carbon atoms through strong covalent bonds known as sigma bonds. These bonds occur due to the sp2 hybridization of the carbon atoms. In sp2 hybridization, one s orbital and two p orbitals combine to form three equivalent sp2 hybrid orbitals which lie in a plane and form bonds with adjacent carbon atoms. The remaining unhybridized p orbital, perpendicular to the plane, overlaps with the neighboring p orbitals to form a pi bond, contributing to the stability and unique electronic properties of carbon nanotubes. This arrangement is similar to that found in graphene, the two-dimensional sheet from which CNTs are derived, and is responsible for many of the remarkable mechanical, electrical, and thermal properties of CNTs. Carbon nanotubes adopt a cylindrical shape because they are essentially graphene sheets rolled into seamless tubes. This rolling process is energetically favorable as it minimizes the surface area and maximizes stability, creating a hollow structure that can vary in diameter and length. Carbon nanotubes are primarily categorized into two types based on their structures: single-walled carbon nanotubes and multi-walled carbon nanotubes. Single-walled carbon nanotubes. This consists of a single layer of graphene rolled into a cylindrical shape. Their diameters typically range from 1 to 2 nanometers, making them ideal for applications requiring high surface area and unique electric properties. Carbon nanotubes become semiconducting because of how their atomic structure affects the behavior of electrons within them. These tubes are formed by rolling a sheet of graphene into a cylinder. The direction and angle at which this sheet is rolled is called chirality, and it determines how electrons move through the nanotube. If the chirality causes the electron paths in the carbon lattice to misalign with certain energy states, it opens a small energy gap between the valence bond and the conduction bond, known as band gap. This band gap blocks electrons flow at low energy, making the nanotube act like a semiconductor, just like silicon in your computer chips. But if the sheet is rolled differently, the energy states overlap and the nanotube behaves like a metal instead, freely conducting electricity. So the reason CNTs can be semiconducting is because their atomic structure controls the energy pathways that electrons can follow, and this is all based on the precise way the graphene is rolled. Chemical vapor deposition is a widely used method to create thin films or nanomaterials like carbon nanotubes by depositing materials from a gas onto a solid surface. In this process, a substrate is placed in a high temperature chamber, and gases containing the desired chemical elements, such as hydrocarbons for carbon, are introduced. When these gases reach the heated surface, they break apart and the atoms settle onto the surface where they react or decompose to form a solid material. For carbon nanotube growth, metal catalyst particles on the substrates help guide carbon atom to form cylindrical tube structures. CVD is popular because it allows for precise control of temperature, gas flow, and material quality, making it ideal for producing uniform and high purity nanotubes on a large scale. The process begins by preparing a substrate, usually a flat surface like silicon or quartz, and coating it with a thin layer of metal catalyst particles such as iron, cobalt, or nickel. These metal particles acts as a seeds where the carbon nanotubes will grow. The size of these particles also helps determine the diameter of the nanotubes. The substrate must be clean and evenly coated to ensure high quality growth. Next, the prepared substrate is placed inside a chemical vapor deposition chamber. This chamber is a special furnace that can reach high temperatures, typically 600 to 900 degrees Celsius. A carbon-containing gas, commonly methane, is introduced into the chamber along with the carrier gas like hydrogen or argon. The high temperature causes the carbon gas to break down, releasing individual carbon atoms into the chamber. As the carbon atoms settle, they land on the metal catalyst particles and start forming carbon bonds. The atoms arrange themselves into a cylindrical structure, growing upwards or sidewards depending on the process conditions. Over time, these atoms continue bonding in a hexagonal pattern, forming seamless tube-like structures, carbon nanotubes. The length, thickness, and quality of the tubes depends on the reaction time, temperature, and gas flow rates. Although semiconducting carbon nanotubes have incredible potential for electronics, we can't fully integrate them yet due to a few big challenges. One major issue is scalability and manufacturing integration. It's very difficult to produce carbon nanotubes in large quantities, with consistent quality, and even harder to place them precisely on chips like we do with silicons. Currently, manufacturing tools and processes are built for flat, rigid materials, and carbon nanotubes are tiny and tricky to align correctly at a commercial scale. Another challenge is purity and chirality control. Carbon nanotubes naturally form with a mix of metallic and semiconducting types, depending on how they roll up. To use them in transistors or circuits, we need only the semiconducting ones. but separating them perfectly from the metallic ones is still extremely difficult and expensive. Until we solve these challenges, carbon nanotubes remains promising but not yet ready to replace traditional semiconductors in everyday devices. Although semiconducting carbon nanotubes have incredible potential for electronics, we can't fully integrate them yet due to a few big challenges. One major issue is scalability and manufacturing integration. It's very difficult to produce carbon nanotubes in large quantities, with consistent quality and even harder to place them precisely on chips like we do with silicons. Currently, manufacturing tools and processes are built for flat, rigid materials, and carbon nanotubes are tiny and tricky to align correctly at a commercial scale. If somehow we do manage to fully integrate semiconducting carbon nanotubes, it could revolutionize many fields of technology. In high performance and energy efficient computing, CNTs could replace traditional silicon in transistors, allowing for faster, smaller, and much more energy efficient processors, making devices like phones and computers more powerful while using less battery. In advanced sensing technologies, their sensitivity to electrical and chemical changes makes them ideal for ultra precise sensors used in environmental monitoring, gas detection, or even wearable health devices. In the field of biomedical equipment, CMTs could lead to a new breakthrough. Because of their tiny size and ability to interact with biological molecules, they can be used for targeted drug delivery, biosensors, or even real time imaging inside the body. As a powerful material for electronic components, CMTs offer strength, flexibility, and excellent conductivity, which means future electronics could be lighter, bendable, and more durable, perfect for next gen wearables. Semiconducting carbon nanotubes represent a remarkable advancement in material science, offering exceptional electrical, mechanical, thermal, optical, and chemical properties that could transform the future of electronics, medicine, and engineering. While challenges in scalability and chirality control have slowed down their integration, continued research and innovation hold the promise of overcoming these barriers. If successfully applied, carbon nanotubes could unlock a new era of high performance, energy efficient, and flexible technologies across many industries. Thank you for listening, and I hope this report has given you a clear and inspiring view of the incredible potential of semiconducting carbon nanotubes.